Soluble in different types of ionic compounds. So what is solubility? The ability of one chemical to dissolve in another. Now, typically you're dealing with water. 99% of the time it's going to be water. So the ability of a substance to dissolve in water. So if it can dissolve in water, we call it soluble. If it can't, we call it insoluble. Another way of putting insoluble is also precipitation. See, precipitation may associate with rain, weather, but for chemistry, it's related to formation of a solid. So if you have a precipitate, you actually have a solid. So for ionic compounds, those that come together to form a solid or a precipitate are said to be insoluble. So what's going on? Well, you have two chemicals. You have this little container. Let's say you decide to add NaCl. And let's say you decide AgNO3. So when you put into this bottle or container of liquid, we'll say it's water, you have both solids initially. The Na breaks apart into sodium ions and chloride ions, so you have your cation, your anion, and then the silver and nitrate does the same thing. Now, the reason they dissolve in water is because they're more attracted to the water than each other. So give me a comparison of this. Let's say you have copper sulfide, which is something that's insoluble. If you put copper sulfide in water, it's going to say it's copper sulfide. Copper and sulfide like each other when they like the water. So what happens? They stay together. You just have this little chunk of solid just hanging out, doing nothing. In comparison, these are soluble, which is saying basically that they like the water more than they like each other. So now they're in water. They see each other, right? And they interact. So it turns out that sodium and nitrate don't like each other in comparison to water. So they have a choice between water and each other. They're like, we'll go with water. So they stay apart. So they're soluble. They stay soluble. So you don't form a solid between sodium and nitrate. But if you get silver and chloride near each other, they do form a solid. They form what's called silver chloride. And that's what we call an insoluble substance. So silver and chloride like each other more than they like the water. As a result, they form a solid. So that's what it really comes down to. What do they like more, each other or the water? In the case of sodium chloride, they like each other more. So things that are insoluble like one another more than they like the water. Whereas things that like the water more are said to be soluble. All right, so here's some rules to help you along with this, because it's impossible to sit there and memorize every insoluble substance, so it'd be a waste of time. So there's rules for it. So there's basically three rules. It's a hierarchy. Rule number one takes part of rule number two over three. So you look in that sequence. So rule number one says the things that are soluble are ammonium, acetate, perchlorates, alkali metal, that's all group one, and nitrates. So for those that have not completely memorized your polyatomic ions, perchlorate looks like that, acetate looks like this, ammonium looks like this, and nitrates look like this. Now, how do you memorize this? Well, another way of memorizing it is I'm a soluble pan. So what the heck does that even mean? Well, the lowercase letters that are not in bold are not the identities of the substances, whereas A is, so that refers to ammonium, A, acetate, soluble, no boldface, so it's just there to help you remember the other ones, pan, P-A-N. So what's the PAN stand for? Perchlorates, alkali metals, and nitrates. So it's easy to remember. So whenever these chemicals are present, you are always soluble. Always. Just automatically, you see one of these, soluble, move on with your life, because there's nothing else to look at. All right, what about when rule one does not apply? Compounds having anions with a -1 charge are soluble unless. So -1, by and large, is soluble, but there is exceptions. So if you see these hydroxide, bromide, chloride, iodide as the anion, you look at it more carefully. If it's anything else with a -1 charge, soluble. Move on. But you don't have to analyze it. That's the way it works. So the way you remember this is O-bricyl. So O stands for hydroxide, BRICL is the bricyl part. So hydroxide is only soluble with alkali metals and calcium, barium, and strontium. So for hydroxide, whereas majority of -1 things are soluble, hydroxide are a little different. They're only soluble with alkali metals calcium, barium, and strontium, CBS. That's the only time they're soluble. So guess what they are the rest of the time? You guessed it, insoluble. Iron 2 hydroxide, insoluble. Copper 2 hydroxide, insoluble. Anything that's not calcium, barium, strontium, or alkali metals is going to be soluble. Excuse me, insoluble. It's going to be insoluble all the time. So, easy way to remember it, hydroxides don't like alkali metals in CBS. So, what the heck does that mean? Remember, if the ions like each other, they form a solid, right? So, they don't like each other, they don't form a solid. So, hydroxides don't like alkali metals, so that means they're going to be soluble with alkali metals, and they're going to be soluble with CBS, calcium, barium, and strontium. Where are they going to be the rest of the time? Insoluble. All right, chlorides, bromides, iodides only form solids with silver, lead, and mercury 1. Mercury 1's weird. That little 2 on the bottom, that's mercury 1. If I give you Hg2+, that's mercury 2. So that little 2 subscript is part of the formula. You just write it in. You don't crisscross. You don't reduce it. Nothing. Just write it and call it a day. So when you see that particular one, you are insoluble. So chlorides, bromides, and iodides typically soluble unless they're with these three, in which case they're insoluble. So how do you remember this? Brickle is a happy solid. Br and Cl. Bromide and chloride is a HAP. H standing for mercury 1. A standing for silver, and then lead positive 2 being your P part, and the other PY is just there to help you remember it. This is lead 2, not lead 4. Please don't confuse them. All right, compounds involving anions with a -2, -3 charge are insoluble. Pretty much all of them are insoluble. So if you see a -2 or -3, you're going to say insoluble. One is the only time you look at it carefully, only time if it's sulfate. Because sulfate's weird. Instead of always being insoluble, it is almost always soluble instead. So it's a flip-flop. When is the situations where sulfates are insoluble, like the rest of the -2, -3s? The only time they're insoluble is with calcium, lead 2, barium, and strontium. The rest of the time, they're not. So how do you remember it? Sulfate is a solid cartoon on PBS. Sulfate, solid. So that's a tip-off. These are the solids. Cartoon, C standing for basically your calcium, PBS, channel, being your lead, barium, and strontium. So that's the only time it's solid. What is it sulfate the rest of the time? Soluble. So a couple different rules. You have to sit there and memorize and get it internalized to make it automatic. So how do you approach questions about solubility? 1, look to see if the cation is ammonium or group 1, which automatically in my case is soluble. So if we see group 1 or ammonium soluble, you're done. Move on. If above does not apply, then your focus is going to be the anion, because that's what's going to determine if you're soluble and insoluble. So the only time you focus on the cations is group 1 and ammonium. The rest of the time, you focus on the anion, and then you have your Brickle rule, your happy solid, you have all those different rules you have to sit there and memorize so you can apply them appropriately. So here's some questions for it. So remember, sulfate is usually what? Soluble, right? So in this situation, what is it? Is it soluble or insoluble? Well, it's not solid cartoon. It's not a cartoon on PBS here, because Mg is not one of those. So this is going to be soluble. Barium chromate. Chromate's a -2 charge. So what is -2, -3 usually? Insoluble. So this is going to be soluble. We'll put I for insoluble. Mercury chloride. Now, you may look at this and say, oh, that's mercury 1 chloride. No. Mercury 1 chloride is a little 2 there. There's no 2. This is mercury 2 chloride. So this would be soluble. Mercury 1, insoluble. Mercury 2, not. Iron 2 hydroxide. Remember, hydroxide usually are insoluble. This is not one of the exceptions. So we're going to call it insoluble. Barium sulfate. Sulfate is usually insoluble with cartoon PBS. Barium is that B in PBS. So this is actually insoluble. PBS, -2 charge with -2, -3, usually going to be insoluble. That's a simple rule to remember. If it's -2, -3, you pretty much almost always are insoluble. Only exception are sulfates. MgO, -2, well, insoluble it is. Because you notice in each of these situations, it's not ammonium or group 1. That's why I could do this. And then last one, iron 3 phosphate. Iron 3 phosphate means phosphate -3 charge. That's going to be insoluble. All right, The other thing we're going to talk about is types of bonding. So what is covalent bonding? It's between two nonmetals. And what happens in covalent bonding, the atoms share electrons. You see what's going on in the diagram? See how those two elements are now sharing their valence electrons? That's what covalent bonding is, when you're sharing electrons. Examples, CO, H2. How do I know this? By looking. Two nonmetals. Remember, the right side of the periodic table is where all your nonmetals are, except for hydrogen, which is on the right side. So hydrogen would be part of this, be a covalent bond. But these two in particular examples, hydrogen being the left side, that's a nonmetal. CO, they're both on the right side. That is a molecular compound because they're both nonmetals. So if you see two things from the right side of the periodic table, automatically going to be molecular compound, which means they automatically have covalent bonding. Also, anything in living objects is going to be covalent. Your skin, your DNA, anything you can name that's living is going to be a covalent bond because those are molecular compounds. So compounds made are called molecular compounds. So molecular compounds and covalent bonds are synced up, so they're related. Metallic bonding is a little different. Bonds where valence electrons are free to move around, which is why metals collect electricity and heat so well. So with metallic bonding, the electrons are not forced to stay in one place. They can go wherever they want to. This is what makes metals such good conductors of electricity, because electrons are able to travel through them very easily. In case you did not know, electricity is nothing more than a movement of electrons. So metals are very good at letting their electrons free. So as a result, they are going to be good conductors. Subsequently, this bond can be bent without breaking. That's another characteristic of things from metallic bonding. Ionic bonding, you basically have what's called electrostatic attractions, opposites attracting. And the way an ionic compound works, it's a crystal structure. You don't have just one Na and one Cl for salt. You have a whole bunch. Each Na is surrounded by 6 chlorides. You could see 1, 2, 3, 4 here, and then you have to realize that three-dimensionally, you would have one in front and one behind that you can't see. So that's actually going to be 6. So each ion is surrounded by 6 anions and vice versa. And that's what makes ionic compounds unique, is that they have this alternating charge setup. You don't see chloride with chloride, you see chloride, sodium, chloride, sodium, chloride, sodium. It alternates. That's because opposites attract and same charges repel. So you don't have two charges identical to each other next to each other. So the differences, covalent bonding is like two dogs, equal strength, aka equal electronegativities, sharing their bones. So each of them bring their bones to the party, each of them bring their electrons, and now they're sharing their bones. That's a covalent bond. Ionic bonding, on the other hand, you have a big dog, you have a small dog, they hang out, big dog jumps, small dog takes the electrons, or in this situation, it's bone away, and now they're attracted to each other because the small dog wants his bone back, so he's going to fall around the big dog. Different electronegativity. Covalent bonding have similar electronegativity, that's why their strength is equal. Here they're different. Remember, metals have lower electronegativities than nonmetals. The metal here is the small dog. That's why you got jump, because the other dog is stronger. And the last kind, metallic bonds, kind of like communism, more or less. Everybody brings their dogs to the party, and everybody shares everybody else's bones. So that's the different types of bonding, and that's how you determine if a substance is soluble or insoluble.